Good evening, and thank you for joining us tonight at the iHeart Pluto Science Speakers Series. My name is Amanda Bosh. I'm a planetary scientist at Lowell Observatory and also the Chief Operating Officer. All week this week, we're celebrating the 92nd anniversary of the discovery of Pluto at the iHeart Pluto Festival. You can find more information about this festival by visiting our website, iheartpluto.org. We have events going on every day and night through Monday, February 21st, so come and join us. Previous science talks are also available to view at the same website or on our YouTube channel. Before we get started, I want to say a big thank you to Karma Sushi of Flagstaff for sponsoring tonight's science talk. So I'd like to, it's my pleasure to give you a little bit of background about our tonight's speaker. Dr. Julien leads the Disruptive Planets group at MIT, whose central mission is to discover and study new worlds to consolidate our understanding of planets and habitats. His primary interest and expertise lie in the field of data science, where math and science are brought together to make sense of newly accessible pieces of reality. Over the past 10 years, he has developed and applied new analysis techniques to map exoplanet atmospheres, to study the radiative and tidal planet-star interactions in eccentric planetary systems, and to constrain the atmospheric properties of exoplanets. Before we get started tonight, I'm going to let our viewers know that you can type your questions into the chat box and we'll pass them on to our speaker. So welcome, Julien, and we're really looking forward to hearing from you tonight about how we might stumble upon life elsewhere.
Great, thank you. Good evening. I'll start sharing my screen, and great, and we will get going. Well, thank you for the introduction, and thank you for the invitation to your science series, World Revealed. I'm really delighted to spend the coming hours with you to talk about the field of exoplanetary science, but also, before that, provide some context, contextualize the past and upcoming astronomical achievements, reflecting on the mission and really the deep potential of space exploration or astronomy. So the first part of this class, the first part of this talk will relate to a course that Professor Richard Binzel, who talked earlier this week, I believe in the series, and I revisited at MIT on the very first year of the pandemic, and that we rebranded our space Odyssey. There's a bit of Odyssey there, and you have the poster here. And the goal of this class is really to provide the student with the scientific foundation and the broader and multidisciplinary context for studying astronomy. And if you are interested in learning more about the experience we designed there, you can use the QR code to reach a website with some information or reach out to me via email later. Great. Now, this being said, we can take off and embark on our very own space odyssey for tonight. Great. So a few years ago, our team revealed the existence of the Trapezoid planets, which are the very first planets that are found beyond the edge of the solar system and are terrestrial, temperate, and thus potentially habitable, and that are in such a configuration that we can study them, study the atmosphere, and search for life elsewhere. Now, these planets were found with a prototype telescope, which is called TRAPPIST, just a simple 60-centimeter telescope based in Chile. And the telescope itself, or the acronym for which it stands, led to the name given to the planetary system, TRAPPIST-1. And first, in this system, we only knew about 2 planets that were really close to its star, and we thought that there was a third planet. And you may have heard of the 2 news releases, but usually the one that people remember, and I'll get to that in a second, is the one where we confirmed that 7 planets really were around this star. 7 planets, and we only got to lift the confusion when we moved from Earth to space using a space-based telescope that you see here, Spitzer, that could stare at the system for 20 days in a row. From the ground, we could only have these sporadic windows catching a transit when a planet was passing in front of the star, and then waiting, catching another one. But it was unclear what was going on, like how many planets were there passing in front of the star. And as soon as we went to space to stare at the system, here you see the first batch of data we downloaded from Spitzer in September 2016. Really exciting time when you actually get this data on the ground. And you can see that just staring continuously at the system for 10 days, we could see all of these dips in the flux coming from the star, each flux corresponding to a moment where one planet, in this case here, it's much deeper, two were passing at the same time in front of the star, actually. So all of this was happening much more than what we were thinking when we were pondering about 3 or 4 planets in front of the star, which allowed us to reveal this system that is a unique opportunity not only to search for signs of life, and we can say that because some of these planets really are temperate. All of them have at their surface temperature, region where the temperature should be such that liquid water could exist. And specifically, some of them, E, F, and G, are in what we call the habitable zone around the star, where the temperature should really, really be mild, so that such condition would not be localized just on the night side of the planet, but all around the surface. Water, if it exists around this planet, and if they harbor an atmosphere, could be in liquid form. And this is the green zone that we're showing here. And you see that this system is quite peculiar, and I'll get to that later in the talk. It is extremely, extremely small compared to our own solar system. These 7 planets orbiting their star, the star TRAPPIST-1, within this tiny portion, the furthest one being about 1/7 of the distance between Mercury and the star. So very unique system that also obviously allows us to revisit our understanding of terrestrial planetary system, where we only have 4 planets. This system has 7 of them around one same star. Okay, great. And so, when we made this discovery, in order to announce it to the world, we worked for about 3 months with NASA, and we prepared a wide range of press material. This stunning poster, a short novel, which later turned into a book. There was also video clips and even virtual reality experience. And I don't know if you remember how that was received by the public. The fact is that it was really, really well received. Like in 2017, the announcement of the discovery was on daily, weekly, monthly magazine, front page of most top news outlets across the world. And the result, well, a substantial fraction of the world population was exposed to the discovery. And why is that? Why is it that the news picked it up and ran with it, and so many people on social media exchange about the discovery? Did we achieve this by working with Cambridge Analytica to boost traffic? Clearly not. The fact is that our species, we really have a special relationship with space. Space drives technological development. It nurtures our imagination. We've looked at it to time plantation, to cross oceans, and to try tackling some really, really special question with regard to, who we are, our sense of identity. Like, where do we come from? Are we alone? All of those. And so the announce of our discovery spread all over the world because it taps deep into our imagination, and it is a small step towards a tangible answer to this fundamental question. And in fact, I believe that it is more than a small step. Sorry about that. It is, I believe, more than a small step in the sense that I feel that it is a reminder of how close we are to an answer to these fundamental questions. I believe that we are on the verge of stumbling upon life elsewhere, be it under the surface of Mars, under the ice crust of Enceladus or Europa, within the clouds of Venus, or around exoplanets such as TRAPPIST-1. We are about to stumble upon life elsewhere. it is inevitable. Inevitable as the pace at which we are growing aware of our surroundings matches the pace of our technological development. And 2017 really was an excellent example of this. The detection of the Trapezoid planets, the first temperate terrestrial exoplanet that we could really study with upcoming observatories, was followed of two other firsts. The first of an object coming from the outside of the solar system, an interstellar object, and the first of the gravitational waves, which were predicted 100 years ago. Now, these three eras of astronomy, temperate terrestrial exoplanets, interstellar object, gravitational wave, opening just a few months apart from each other, really reflects perfectly the continuously increasing pace of our awakening to the universe. Now, we are awakening more as well as faster. And as a result, we are getting increasingly closer to this key step on our Odyssey, stumbling upon life elsewhere. Okay, great, job done. But wait, what are you going to do about it, right? And this is really what I'm passionate about, like trying to create a space where the necessary pondering can emerge and we can try to prepare ourselves in order to make the best of this extraordinary milestone. Just make sure that it counts. Why is that? Well, at a time where our species and our ecosystem face challenging ranging from political crisis to large-scale malnutrition, overpopulation, endangered species, climate change, pandemics, existential stresses, it seems essential that we aim to leverage to its maximum potential any opportunity to reflect on where we're at. Naturally, astronomy itself, nor astronomers, are going to provide us with a solution to all these problems, but it may provide us with a unique opportunity to seed changes. When Copernicus claimed that the Earth was not at the center of the universe, it triggered a revolution through which religion, science, and society had to adapt to this new worldview. And I do see a convergence between the tension points calling for a new worldview and upcoming experiences that may contribute to it. Carl Jung, the founder of analytical psychology, said that every superior form of consciousness needs a worldview. That every increase in knowledge and experiences is a step towards its development. And as it shapes its worldview, the being that thinks transforms itself. I'm seeing things in the chat, so if there's any interruption, please jump in. Great. Now, I wish for us to prepare to really take these upcoming experiences in. I wish for us to intentionally consider what it means to be the conscious dominant species on this planet. We've climbed a lot of level of emergences, from family to tribes, cities to counties, states, nations, and doing so, we've brought more and more of us together via shared values and stories, narratives that could define one family, one tribe, one nation from another, us versus them. So could it be that finding another them, separated from us by a vast amount of empty space, would bring our perceived sense of us to a different level of emergence at the planetary level in some sort? Somehow our commonalities and responsibilities as the conscious dominant species, then underlined by this new us, becoming the foundation upon which we would be making our stand. As Carl Sagan said in his famous Pale Blue Dot speech, our planet is a lonely speck in the great anthropic cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Like it or not, the Earth is where we make our stand. The mission of astronomy has been to help us understand our environment and how we fit within it. It is a unique tool that helped us navigate the world outside, as well as the world inside of us, so the outside world and our inner world. 10,000 years ago already, it helped us, not us, but our ancestor really, understand, track, and predict seasons. The Warren Field calendar, which you see here on the screen, is to be found in Scotland, and it is a Mesolithic monument that contains a series of 12 pits, which appears to help the observer track the lunar months by mimicking the phase of the moon. It also aligns at sunrise at the winter solstice. And what this allows for, it allows for the cycle of the moon and of the sun to be coordinated or synced. What's really fascinating about this monument is that it has been reshaped over 100 times to account for shifts in these cycles. And these modifications, these updates, have been happening over the course of 6,000 years. So it emphasized the extent to which the humans at the time were really already aware of the importance of the knowledge that they could be receiving from the sky. And what's fascinating is that this calendar is predating the first agricultural revolution in the area by at least 5,000 years. So the calendar was actually used by hunter-gatherer to predict the availability of food, such as berries on the bushes, fish back up the rivers, rather than helping cultivators with the timing of plantation. So thinking of disruption, one can wonder if such tools could have contributed to spark the first agricultural revolution in some parts of the world. Now, if we fast forward by about 8,000 years, we can find the central contribution of astronomy in society all around the world. Sorry, this is moving around here. There we go. Thank you for your patience. Now, from the calendar 3 millennia before the Common Era in India to the remarkable alignment of Egypt's pyramid to the polar star at the time. With the arrival of a new capability of recording information, writing, stellar catalog appeared. The first one goes back at least 1,200 years before the Common Era in Mesopotamia. There, the astronomers were priests, scribes, specializing in astronomy and other forms of divination. So looking back, one can confidently say that astronomy has contributed to 3 pillars of our society in some sort. It has helped us first develop our vision of the outer world, things that helped us with food, environment, things that are directly related to our physiological needs. And then astronomy has helped us develop our vision of our inner world and sense of self, imagination, spirituality, these higher concepts that have brought us together, these themes that are directly related to our psychological need as conscious being. And third, astronomy has helped us develop the tools that connect both of these worlds. And this is, I think, where science and technology comes into play, this interface. So outer world, inner world, and the tools that really connect the two. Some examples. Astronomy has enhanced our agriculture. It has helped predict season-related events such as the flooding of the Nile. The sky, both inaccessible and full of knowledge, became the home of gods throughout many cultures. Early culture identify celestial bodies with the gods themselves, and the motion in the sky became prophecies of what was to come. Cultures such as the ancient Maya appeared to have timed many of their great battles according to the planet they connected to the god of war, Venus for them, Mars for other culture. So most culture throughout human history have turned to the sky and attributed to it similar higher power. Later, again, fast forward, the periodicities and cycles of the planet and stars were intellectual seeds for the mathematics, keeping track of time and predicting the future configuration of the cosmological clock related to scientific and technological development. 2 examples coming from the ancient Greece. The first 3D geometrical model for planetary motion was created in 400 BC. And the mechanism that you see now, the Antikythera mechanism, that is the first ancestor of the astronomical computer, and it is actually dating from 150 before the Common Era. It was discovered in the 1900s, and it is of interest for 2 reasons. First, it uses a differential gear, which you see here, which was previously thought to have been invented in the 16th century. Second, the miniaturization of the pieces and the complexity of the parts is comparable to clocks that we had seen before in the 18th century. So you see the extent to which predicting the configuration of the cosmological clock really drove technological development there. Now, astronomy has had also an important impact, it has had an important impact on all of this theme, owing to the fact, I believe, that it has three fundamental qualities. It is, space has. Space is captivating, humbling, and disruptive. Captivating? Of course. Which adult has never spent at least 10 minutes simply staring at the night sky? Why? If you ask people across the globe to name a telescope, they would, until now that James Webb is launched, it may change, they would say Hubble, if not for the captivating nature of such images. Humbling? Disruptive? Surely, owing to what I would call decentering experiences. Early on, we grew to believe that we had a privileged position in the universe. In addition to that, time after time, as we created worldview, we held very, very tight on, failing to acknowledge the limitation of the information we had at the times when we created this worldview. We moved from flat Earth worldview to round Earth worldview, from geocentrism to heliocentrism. Fast forward, a new reference to Hubble again, who provided, as you saw in the image just before, even references for our own galaxy, the Milky Way, one amongst hundreds of billions, each of them containing hundreds of billions of stars like our sun, each of these stars likely hosting more than one planet. And as we're talking about planets, allow me to follow up and discuss a bit what's happening in our field, the field of exoplanetary science, which study planets around other stars than our sun. So, this is one screenshot from our group's website, as mentioned before, the Disruptive Planet groups. And one of the focus of the group, one of the quests relates to discovering new worlds. And so why is it so important to discover worlds outside the edge of the solar system? Well, the thing is, for centuries, our perspective on planets, planet formation, has been based on one unique sample, our solar system. And it's true that we build remarkable formation and evolution theory, and surely they fail in some way at predicting everything we were to find when we look beyond our local neighborhood. And I mean, from a star point of view, not at the universe level. The outcome of a political election cannot be predicted from surveying a few individuals from the same family, right? These are surely different people, but they share history, somehow values as well. And the same happens with a few planets found around one star. Yes, there are different planets, but they were formed at the same time around the same star. And so there's only so much they can tell us about the process of being formed and evolving, all right? So as we started to look beyond the edge of the solar system, our perspective broadened and our theories were challenged. We notably, actually, let me show you a few examples before I dive there. We found planets without star, literally free-floating through the galaxy. We found planets with multiple stars, such as Kepler-16b, that has 2 stars and offers this iconic double sunset, such as Tatooine in Star Wars. We found planets such as J1407b that has 37 rings with an extent about 200 times those of Saturn, meaning that if Saturn had such rings, it'll be bigger and brighter than the moon in the sky, so we'll be able to see it by naked eyes. We found planets that are literally dying as we speak around their star, being pulled apart by the differential of gravitational field just over the course of their diameter. So that's how much diversity we found when we started looking elsewhere. And now that I've clearly made that point that looking elsewhere is worth it, as we find things that are new, and it forces us to think about the theories and the worldview we've created. Let me provide you with a bit of history on our field. And if there are questions, please do jump in. I cannot check the chat. On this poster, which is part of the Exoplanet Travel Bureau poster, there are really two fantastic poster series that, if you're not aware of, you should check. The Exoplanet Travel Bureau series, as well as the Vision of the Future series. Both are poster series designed by NASA's team, and they are fabulous. And on this poster, you can see a few planetary a few systems. Not all of them are actually planetary, but a few systems. And this 151 Pegasi b is one that you probably have heard of, because it is the one that led to the first Nobel Prize given to the field of exoplanetary science, specifically to the Swiss Michel Mayor and Didier Queloz, for the discovery of an exoplanet orbiting a solar-type star. And that was in 2019. And in order to contextualize that discovery, I'll show here the planet found. On the left side is a function of their mass in Earth's mass, and as a function of their orbital period in days, so how long they take to go around the star. And then here I'll be showing the planet's size in Earth's radius, and again, the period. To provide further structure to this information, you'll see in red the planet in our solar system: Jupiter, Saturn, Uranus, Neptune, down to Mercury. The line that is here is a line that leads to the transition between planets and what we call brown dwarfs. So if the mass is high enough at the center of the body, you might be able to kickstart the fusion of deuterium. And we start with 51 Peg B in 1995. We have its mass. And bear with me, you'll know why in a bit. We don't have its size yet. Okay, all right. So as we move forward, actually, before we move forward, let's move backwards. What we see is that there are quite a few objects that were actually detected before, right? We have a PCR 1257, 12C. Yes, names are, that's another discussion. So this is another set of planets, all flying around the same star. So the same object, PSR 125712. This is the first one, B, C is the third one, and D is the fourth one. Okay, detected, not necessarily the closest to the object, but again, discussing names is a whole other 20 minutes. We'll need to take care of that. So I'll move forward and explain why 51 Peg B was so important back then. Well, PSR, which was an ensemble of planets found, 3 of them in 1992, were actually not found around a main sequence star. They were found around a pulsar. So on this dramatic posters, they were qualified as zombie world because the star was, died, even so it said undead. It went through the process of shedding its outer layer, and what was left was a pulsar. So these worlds were qualified zombie world in the sense that they were not found around the classic main sequence star as we would think of when we think of the sun. Other worlds, such as this one, HD 114762b, was detected, confirmed, but its mass is actually likely too high for it to truly be a planet. It's likely a brown dwarf. While this one, detected in 88, Gamma Cephei AB, had the right mass, but it took 14 years to confirm these planets. So you could imagine that back in the days, finding a signal that could hint at the presence of a planet around a main sequence star was quite an adventure and a thrill to get to a point of really confirming the planetary nature of the planets. And now that this historical foundation is set, we can move forward in time and see what happens. So we're gonna just fast forward. We have the first planet that is actually seen in transit, and so we can get its size, and I'll get to it in a second. But really, if we zoom in, these are the populations that are not fully up to date, but almost. And you see that from one sample, one planetary system with 8 or 9 planets, I heart Pluto, so I think we can I'm not going to comment further. But from a handful of planets here in the solar system, we went up to over 4,900 planets as of today in 3,700 planetary systems. So a substantial increase in sample size. Now, of course, we don't know the property of this planet as well as we do know the property of the Earth, Mars, and others around. Still, it provided us with some really interesting insights, which you can already grasp right here, right? We have been able to provide constraint on the Milky Way population, which is great. But also, and most importantly, we've revealed these new planetary types that do not have analog in the solar system. We find planets as big as Jupiter and Saturn turning around the star in only a few days, in comparison to Jupiter and Saturn that are doing so in 11 years for Jupiter. And these are called hot Jupiters. What's interesting, and I'll get to that, is that these giant planets, which are composed of roughly 90% hydrogen, were thought to be found far away, far away from their host, which is where you can find enough of this material beyond the ice line to form these giants. And so it challenged us to think about how these could be formed. And we also have the same, not necessarily the same problems. It's easier to conceptually predict those, but we don't have any analog in the solar system. So we found this dominant planetary population with sizes between those of Venus and the Earth, the largest rocky planet in the solar system, and Uranus and Neptune, that are these ice giants. So there's these two new, and we call them super Earth. But in fact, if we zoom into this distribution, we do find that it's a bimodal distribution where we have large rocky planets that we would qualify as super Earth that have up to 1.6 Earth size, and we have mini Neptune that are a smaller version of Neptune. So these are absolutely not observed in the solar system. Okay.
So Julien, I'm going to just
Thank you.
Interject here for a second, if you don't mind. We have a question from somebody asking about what kinds of data you gathered to learn about these planets.
Perfect.
And in addition to just finding them, but also learning about what's on them, composition.
That's a great question. So first of all, thank you for interrupting. I was seeing message in the chat and I didn't know if I should read it or not. So thank you. And then with regard to the question, if we can wait a tiny bit, I'll get to it. Sure. So right now I'm just going to do the whole, hey, we're discovering them, but how do we actually get to discover them? And then I'll discuss the characterization.
Okay. And
thank you for the question. Yes.
We also have a question about the pulsar planet. And so if you would like to wait on that one as well, we can do that.
What is the question?
Is it going through the radiation belt of the pulsar?
Ooh, that is a great question. My first answer would be, I don't think so. They are quite far from it. But I am not 100% positive. I'm sorry. I've not worked on this planet and I focus mostly on planet around the main sequence. So I'm not versed into the distance at which this radiation belt would be found.
Okay, thank you.
Thank you for the question, though. I'll make sure to look into it for my next talk on the topic. Thanks. So with regard to these hot Jupiters, what we realize is, okay, well, this is usually how we think of this. We have planets like Jupiter forming far away from the star, and now we have to find a way to get them to move closer. So it forces us to think about different migration mechanism, or to consider if there is a way for the planet to form close to their star, despite the fact that we always put the ice line much, much, much further away. So it forces us to play with mechanism. I mean, when I say play conceptually, play with mechanisms that were not really investigated to that extent prior to us finding these planets, which makes sense. There was no reason to look further into these. And so to dive further into the data that support this discovery and then further the characterization, how do we detect or study exoplanets, right? Sorry about that. There we go. So there's a fundamental difference when we think of planets versus exoplanets. And I believe you probably spent a bit of time in the solar system earlier and throughout the week. So I will express appreciation for these pictures where we actually get to see spatial characteristics such as rings and zones and bands on Jupiter's. So all of those things are beautiful and captivating, and so not like what we find when we're dealing with exoplanets. Because when we deal with exoplanet, this is an exoplanetary system, HD 189733b. In most cases, unless you're doing direct imaging, and I'm not going to talk about this here, you can zoom as much as you want with biggest telescope possible, and all you get is really just a few pixels brightened up by all the flux coming from the planetary system and being condensed on these few pixels. So there comes the question. Yeah, we have great posters to compensate for that, yes. How can we study a whole planetary system from one bright dot, right? Well, we're lucky because that bright dot has a flux that change over time and wavelengths. And by wavelengths, I mean color. And this is really by studying the flux variation over time and wavelengths that we can start disentangling between the contribution of a planet, of a star, and doing a lot of amazing things that I'm going to introduce to you, Yep. All right, so the first thing is when two objects co-orbit one another, they really co-orbit the common center of gravity. And so even if you have a small planet and a star, the star is still going to wobble around the common center of mass. And as the star is moving towards you and then away from you, it's going to be going through a process of Doppler shift on its emission spectrum. And you can see this on the image. At the bottom is a synthetic emission spectrum of a star with different absorption line. And you see it move towards the red when the star is moving away from us, and then towards the blue when the star is moving towards us. And this motion of the spectral line with wavelengths gives us information about the mass of the companion. And also the periodicity of the signal obviously gives us information about the orbital period of the planet. Now, when we move towards another technique, the transit technique, what we're searching for are these periodic flux drop when a planet passes in front of the star. And from this flux drop, we can get the planet to star area ratio. So we can get constraint on the size of the planet. Now, quick aside, the reason why TRAPPIST-1 was so special and it allowed us to find these temperate terrestrial planet around it is because it's really, really small. It's 10 times smaller than the sun. So the size of the fraction of its area hidden when a terrestrial planet is in front of it is 100 times larger than when such a planet would be in front of the sun. And in fact, TRAPPIST-1 is about the size of Jupiter. All right, so this is how we can get to find these terrestrial planets, by looking for them around what we call ultra-cool dwarf stars. Now, if we keep on going, when we have a planet for which we can get the mass and the radius, we can get the density, so we can start discussing bulk composition. And on this graph, you see an ensemble of planets as a function of their radius and their mass. And naturally, if they have, for a given radius, a heavy mass, you will only be able to explain them if they are mostly composed of iron. If for the same mass they have a much larger radius, you'll be able to explain them as being a planet with their primordial envelope. They still have a cold hydrogen helium atmosphere around them. And I won't go into the detail of this plot much further, this curve being isocompositional curves. Okay, and each of these planets, each of these dots being planets with uncertainty on their mass and uncertainty on their radius, color relating to what we call effective equilibrium temperature. Okay, so the fun thing is we can go beyond that, just looking at this bright point, and we can even map planets. All right, so how can we map planets if we cannot even resolve the star? If the star itself is one point and we cannot distinguish different parts of the star, searching for spots and so forth directly, how can we map a planet with that little information? Well, again, looking at the variation of the flux, the function of time and wavelength, which is nicely represented here. When the planet is passing in front of the star, we have a drop of the flux as a function of time, which I just introduced earlier, transits. When the planet, if it does, depending on the orbital configuration, passes behind its star, we have what we call an occultation, which is going to be very shallow if the planet is cool, right? The occultation in the infrared will be related to the thermal emission of the planet, in the visible to the reflection, which scaled down very quickly with the distance to the star. And then what we have between these two relates to the flux of the planet as a function of its hemisphere. If the planet is close enough, we have what is called tidally locked planets. Just as the moon always shows the same face to the star, these planets always show the same hemisphere to, the moon to the Earth, the planet to the star. Okay, so we're pretty much looking at the planet rotating upon itself during one orbit. So we can do that to create what we call, to obtain orbital phase curve. So the flux as a function of the hemisphere, and at 0.5 is when we have the eclipse, the planet disappear behind the star, and here is a transit, the planet pass in front of the star. So what we can start to do is look at here, because we're working in the optical, we're looking at reflection patterns at the surface of the planet. And we can look for planets that have these types of very unique features, such as Kepler-7b, where we have part of the planet that is quite reflective, and then past the substellar point, 0, 0 here is the point of the planet that's always facing towards its star. We have a drop in reflectivity, which allows us to dive quite deep into the atmospheric property of this planet, allowing us to grasp that for this planet, we have one side of the planet that is continuously under thick cloud coverage. And the story goes as follows. Parcels of air that are hot are brought by supersonic equatorial jet to the night side, permanent night side, where the temperature drops enough for cloud particles to form, magnesium silicate dominated cloud particle, and we can tell that from the temperature that we are expecting on the night side of the planet. And then they are brought back to the night side, again by these supersonic winds that are just going around the equator of the planet, where they reflect the light of the star up to a point where the parcel of air is warmed up enough to lead to the sublimation of these cloud particles, and so you keep on going. So just through these simple measurements, we can get into a pretty good understanding of the processes of some of this exoplanet atmosphere. And I'll skip this example here in the infrared to go straight to another technique that is of interest, transmission spectroscopy, because it relates to the question that was introduced before. How can we dive deeper? What are some of the techniques? And I'll get into a bit more details for this one, where we're looking at more than just a flux drop related to the planet during a transit, but we're also looking at the wavelength dependent effect of the atmosphere. Because when a planet passes in front of a star, a tiny fraction of the stellar light is going to go through the planet atmosphere and record information on how the different components of the atmosphere are going to interact with the stellar light. So what you can see here on the left is a schematic view or depiction of what is happening when we have an atmosphere that is mostly transparent at a certain wavelength, lambda 2, so there's a low atmospheric absorption, and there is quite a bit at lambda 1. So the wavelengths at lambda 2, the atmosphere is going to appear as transparent but opaque at lambda 1, meaning that the flux drop during transit will be slightly deeper at lambda 1 than it is at lambda 2. And these are these variation, these wavelengths dependent variationist transit depths that are going to inform us about the atmospheric properties. So what you see here is a transit depths as a function of wavelengths for Hubble observation between 1.1 and 1.7 micron. And you see that the planet appears to be bigger, right? The transit depth is deeper, so we can convert that into planet size. The planet appears to be about 1% or so bigger, around 1.4 micron. So you can turn to you friends with excellent knowledge about some spectroscopic information, and that person will tell you that, hey, actually, you know, what's likely happening here, as I don't see anything around 1.2, it's not methane that's playing with this signal, but it's actually water. So here, water is contributing to the planet appearing slightly bigger in transmission, around 1.4 micron. And so, again, the beauty of such technique is that it directly relates to the planet to star area ratio, right? So if we want to study small planets, we turn to small stars. And still till today, despite the fact that these planets were found, the TRAPPIST-1 planet in 2017, these planets are still today the best planet to search for or to study terrestrial planets and temperate terrestrial planet atmosphere, right? In the temperate regime, these are the ones that are going to have a signal and transmission the largest, and with a signal to noise ratio the largest compared to all other terrestrial planets. So what we can do, we can use some of the facilities available, such as the Hubble Space Telescope, to start searching for primordial atmosphere, which are these atmospheres that are formed first when a planet forms. So they are mostly composed of hydrogen and helium. And if they are still present around planets like TRAPPIST-1, because they have a low mean molecular mass, which is dominated by hydrogen and helium, they're going to be very thick compared to what they would be if they would be primarily composed of nitrogen or carbon dioxide, which have a mean molecular mass about 10 times to 20 times larger, meaning that the scale height of the atmosphere is going to be much, much smaller. So the atmosphere itself is going to be more compacted. So the atmospheric signal that I was showing earlier will be much smaller, here represented in blue. So we can search for these thick, puffy atmosphere with Hubble, which was done in 2016 for the first planets in the system, and then later in 2017 through now for the last planet in the system. And what we found is that the signal do reject primordial atmosphere. So that means that for the TRAPPIST-1 planet, at least, we have to wait for other observatory to start considering other scenarios of secondary atmosphere. And the reason why I want to end the talk with this is because the best is yet to come. This search, the search for secondary atmosphere, is something that is going to be possible. You see the uncertainty that we have with the measurements of the Hubble Space Telescope, which cannot really inform us about the presence or not of secondary atmosphere. With the upcoming telescope, James Webb, which is now at L2, we will be able to get a signal sufficient to start searching for the presence of secondary atmosphere, be it, carbon dioxide dominated, nitrogen dominated. And so that is what is next for the field of astronomy. And so with these upcoming observatories, we will be able to study the atmosphere of a wide range of other worlds, including terrestrial planets. We'll be able to create maps, not of terrestrial planets, but of hot Jupiters, mini Neptune. And so it will really help us refine our understanding of planets, climates, and I hope key concepts such as the concept of habitats and life, which is really where I think astronomy is going to have a strong impact on our species in the next decades. So in the context of World Revealed, I do hope that through this upcoming milestone of astronomy, we're really going to gain new vantage points from which we'll be able to look back and reflect on our own precious planets. And I am going to leave it at that. Thank you. And I will stop sharing and take any question that may be left.
Wow. Yeah, thank you so much. So much to think about there. That was really excellent. I think that it seemed to me that you touched on the on TP's question, but if you still have any other questions about that one, please feel free to put some more into the chat. And I'm going to just, one of the things that I was thinking about as I was listening to this, and I'm going to invite our viewers to also think about is, what, so many options for what life elsewhere is going to look like. And that's one of my questions for you. And then I will get back to some of the others from the chat as well is, what do you think? What's the first life that we're going to find elsewhere? What kinds of thoughts do you have?
Yeah, that's a great question. So you're right. Life, just as planet and planetary system, is a concept for which we have a very, very small sample to extrapolate from. So I have the impression that life, we are most likely to stumble upon life at the microscopic stage. And it depends if we are considering the one that we may stumble upon through the search for biosignature with exoplanet, or the one that I'm sure Kelsey introduced earlier this week. Dr. Moore introduced earlier this week. And so, yes. So right now, what we're looking for in our field are biosignatures, which would be something that we cannot explain through geological processes, non-sample of gas that are difficult for us to explain. And naturally, the more complex the signature, the easier it is for us to consider that is not produced by such processes, geological processes. So either we finding life at that level, microscopic, and there will be a lot of debate to really disentangle its origin from geological processes, or we find such things as, CFCs but then we get closer to technosignature. And if we find molecules that are complex, then in that case, it'll be easier for us to say it's life and it's actually intelligent life. But we'll see. But you're right, we're coming with our own strong biases. We're looking for signs of life around temperate planets because we need a solvent, and we used to have water as a solvent.
Right. Oh, thank you. Yeah, that was some good thoughts there. So I'm going to just go through the chat here. We have a couple of questions stacked up here. From Keith, he wonders, were Jupiter and Saturn once much closer to the sun than they are now?
Not much closer, no. Not much closer. There's been some evolution with regard to their orbits, but not to the extent that we need to create a hot Jupiter. So they were not formed much closer with days of orbits and then move to years of orbit. There was some evolution. It is thought that there was some evolution, but not to the extent mentioned before.
Not that we're seeing in the other systems. Okay. Mr. Angel says that a recent theory suggests that our early solar system was visited by a wandering star. Could that explain the far out orbits of our gas giants? Should they not be closer to our sun?
Yes. So there's been theories along those lines. It would not have led to our gas giant to move. I mean, they were not affected to that extent. So again, I think it relates to the first question, the question just before. They were not pulled from by AUs. Their orbits were perturbed, but not to that extent. It affected the old clouds and so forth.
Something, a hot Jupiter, that close to the sun would really take a lot of energy to pull it out of that particular orbit. So that's a difficult thing to do. Okay. Glenn asks, does it seem more common that the larger planets form closer to the stars so that our system is kind of an oddball?
So this is Glenn. Yeah. Okay. So I'm seeing the question here. It goes the other way around usually. So the more material. So in order for material to be available for creation, it needs to be in the condensate form. And so giant planets are mostly composed of hydrogen, really. And hydrogen is present in the form of ice, either water or methane ice, beyond what is called the ice line, so quite far from the star. And only there can such big planet be formed. Only there can an Earth-like planet or bigger, a super Earth-like core, gather all that material that is not in the gas form closer to the star, but in these ice form beyond what is the ice line. So larger planets are thought to be found predominantly far from their star.
So what do we need to study, or what information do we need to know to explain all of the hot Jupiters?
Yeah, the information that we need to gather relates to the migration mechanism. I mean, unless these planets form under remarkable processes in situ, somehow they manage to form themselves in a very turbulent environment close to a nascent star, which is quite tricky. We have to consider the mechanism that can bring them in, either migration through a disk that is still forming. The last step of the process will be tricky. The disk will likely be dissipated at a certain distance from the star, or, and this is the dominant theory for most system, the planet is moved on a highly eccentric orbit through tidal interaction, and then the orbital energy and momentum is transferred to the star, and progressively the planet's orbit loses its eccentricity, and so the planet ends up with a semi-major axis that was the distance between the planet and the star when the planet is at the closest on the highly eccentric orbit.
Would we see, I mean, if that were the case, would we see more planets with highly eccentric orbits?
Well, it depends on the timescales for these processes. And so these are processes that are of interest, notably to the group, to consider how the energy can really be transferred between these stars and planet. And yeah, tidal interaction is naturally what comes to mind, but there might be other processes behind that too.
Are there planets right now known that do have highly eccentric orbits?
Yes, yeah.
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 Okay. There we go.
Some of them, yeah. I mean, I think my favorite one is HD 80606b, which is an orbit with an eccentricity of 0.93.
Oh, wow.
So that's comet level.
Yeah. So an eccentricity of 0 is a circle, and an eccentricity of 1 is a non-bound body. So 0.93 is really close. Like, as you said, it's comet level. So it's a very elongated orbit. Yeah. Wow. I was not aware of that.
Yeah, it is a period of 111 days. And at the closest, it passes 6 stellar radii away from the star. So over the course of 24 hours, the atmospheric temperatures goes from, on the side that is close to the star, it passes so close that it goes from 400 Kelvin to 2000 Kelvin in 24 hours. So there's this, the planet received 1,000 times the equivalent to the Levi-Shoemaker impact in terms of energy that Jupiter received. So
wow.
It's, what is great again is that it provides us with new windows. It gets us to study the impulse response of an atmosphere to a gigantic amount of energy, and we can study how the energy is redistributed. So it's interesting to have these bodies available.
Wow, absolutely. Is it possible for you to, do all planets, all of these exoplanets that you're able to study, do they all have atmospheres? Do you see some? How would you know if it doesn't have an atmosphere?
That's a great question. Not knowing if it there is a limitation. It is difficult to disentangle with current technology. It's difficult to disentangle between a planet that has a thick, an atmosphere but with thick haze, and a planet without an atmosphere. And so, with increased sensitivity and spectral resolution, we will be able to get to disentangle between the two of them, but it will require a significant amount of observation time to get to disentangle between these two scenarios.
So it's time, not aperture. So is that something that JWST could help with?
Yeah, I meant to say time in the sense of aperture, just to collect photon. Yeah, it's just sensitivity. Yeah, but it is possible. Not for all of them, of course. It depends on the configuration, but we should be able to get to that point.
Wow, great. And I had one question for you. You said that your group works on disruptive planets, and I was wondering what you mean by disruptive.
Yeah, so the group is named Disruptive Planet in the sense that these exoplanets are there to disrupt our understanding of all of these processes so that we can rebuild them in such a way that is inclusive of these new insights that exoplanet provides.
Okay, so it's really teaching us about using the ones that you're finding to really teach us about the whole family of exoplanets that are out there.
Yeah.
Excellent. Okay. Well, this was just a fascinating talk, and I just can't wait to see what you find from JWST observations as well. I'm sure you can't either. So
yes.
Yeah. Well, it looks like, unless there are any other questions, what I'd like to do is just thank you once again for spending this time with us and sharing all of your expertise with us. Just really a great talk. So thank you very much, and good night to all of our viewers.
Good night. Thank you.